Over the course of this chapter, we've seen many ways to find the maximum and minimum values of a function using calculus. In this section, we're going to work some word problems that involve maximizing or minimizing some quantity using those techniques. We call these kind of problems optimization problems. And we talk about optimizing the particular quantity that we're talking about. Now, the book does write down some guidelines for this, but they're very kind of vague and not very specific. So I think it will make a lot more sense to just go ahead and work through some examples to get a feel for what's going on. Now, in this particular section, the majority of the problems are really more based around geometrical ideas like areas and volumes. In the next section, section 3.5, it will actually be a continuation of this section to some business and economics applications. But that will be in its own separate video. So most of these will be very geometrical based. I'm going to start off with problem 5. Let me just read this straight from the book. An animal shelter has 160 feet of fencing to include. An animal shelter has 160 feet of fencing to enclose 2 adjacent rectangular playpen areas for dogs. What dimensions should be used so that the enclosed area will be a maximum? The first thing we want to do is draw a picture of the situation. So we're going to have two adjacent playpen areas. And the book actually has a picture of this already, and what they make clear in the picture that they have in the book, that they want these to have the same dimension to them. They call that dimension x, and the other dimension along here, y. That's not actually part of the statement of the problem. And if we actually don't take the picture at its word, if we don't have these be the same length here, actually the true answer would be to have one of these have a width of 0, so that the other one basically dominates as one big playpen area. So we're going to follow the picture just because that's obviously what they mean in this particular problem. So we have two playpen areas. We want to find out the dimensions that that use the same amount of fencing, but maximizes the area that's inside of these. Now they've actually already given us our letters. That would be the first thing that we would do after drawing our picture, is label what variables that we actually have. We have dimensions x and we have a dimension y. Once we have that picture and the names for our variables, we want to go ahead and try to write down any relevant equations. The first thing that we want to do is note that we are trying to maximize area. So we're going to have some formula involving the area. What is the area that's enclosed by these fences? Now, we have essentially 2 rectangles here, or really one big rectangle. The area of a rectangle, we just take our length times width. Our length here being 2x, not just x, 2x, and a width of y. So we multiply those together. Our formula for the area is 2xy. The only problem here is that we have 2 variables in this function. So this is not really, we're not treating a as a function of x, we're actually kind of treating it as a function of both x and y. And that's kind of a problem. All of our techniques so far have been working with a function of a single variable. Now, later on in calculus, it's actually possible to break that rule and talk about what we call multivariable functions. But we are definitely not going to be dealing with that right here. That is kind of in a normal calculus sequence, that would be a Calc 3 kind of problem. Definitely beyond what we want to be working with right now. So somehow we need to change this to a function of a single variable. And that's why they give us some other information. They tell us that the total amount of fencing is 160 feet. If we take all this fence and were to stretch it all out, we have 160 feet of fencing to work with. Well, what is the total amount of fence in terms of x and y? Well, keep in mind here we have a copy of x here, a copy of x here, we have 2 more copies of x here, and we have copies of y on both of those. These are supposed to be rectangles, so the opposite sides should be equal to what we already are given. So in total we have 4 copies of x, and we have 3 copies of y. So we have 4x plus 3y as the total amount of fence in terms of x and y. But the text of the problem says that that has to come to 160 feet. So we have 160 feet to be divided up among these x and y in such a way that 4x plus 3y is that 160. We can use this equation, which the book is referring to as our secondary equation, and the formula for the area is the primary equation. I probably won't be referring to it as such most of the time, but that's what the book uses. I can use this secondary equation to essentially replace my y by solving this equation for y, because I know x and y have to be related by this equation. So I'm going to go ahead and bring the 4x over to the other side and divide by 3. Unfortunately, we get fractions in there, but that's kind of what we had to have. So we know that whatever x is, y has to be equal to this, which means I get to go ahead and plug this in for the y that we have here. Essentially, we've turned our area into a function of x, which is equal to 2x times this stuff, 160 thirds minus 4 thirds x. Or really, I'd like to go ahead and actually expand that out. I'll distribute the 2x to both of our terms. The first one, I double the 160 to 320 over 3 times x. Then I double the 4 to an 8 thirds, but now I have 2 x's, so I have an x squared. So that is my function for the area in terms of x. And I want to maximize this thing. Now, before we even do that, we actually do want to limit what values of x we can even talk about. In a lot of these optimization problems, a lot of maximizing problems, if we were to try to work with the entire real line for put any value of x that we want into this function, we could have a lot of things happen. But there's only going to be certain x's that even make sense to be in the problem. The book refers to this as the feasible domain of the function. Essentially, what makes sense for the problem. For instance, in this particular case, x and y are supposed to be lengths. That means they can't be negative numbers. We're not going to be considering negative lengths here. That just wouldn't make much sense to us. So we know that, first of all, well, x has to be at least 0. Theoretically, we'd expect it to not equal 0, but we want to let it go up to that point. That would be the smallest possible thing we could ever let x be. On the other hand, we also know that y has to be greater than or equal to 0. I'm going to set it like this, because I'm going to use the fact that I know that y is equal to this thing. And I can essentially solve this inequality, that 0 is less than or equal to that, to get a different bound on x. Essentially, I can move the 4 thirds x to the other side. And then I could divide by 4 thirds. I'll get rid of the thirds on the bottom, and I divide the 160 by 4 to get that x is less than or equal to 40. Essentially, my feasible domain here is going to be the closed interval from 0 to 40. Those are the possible values of x that we can work with. And this is actually pretty nice for us, because what we're saying is that we have a continuous function, or actually a differentiable function, on a closed interval. And those were the particular cases that were the best to use back in 3.2. Now this has become essentially a 3.2 problem, where we're trying to find the maximum value of this function on this interval. What do we do to find that? By using calculus, we found the critical points by differentiating the function. What is the derivative of this function? Well, a prime of x. Well, here the x goes away. We're left with the 320 over 3. Here we have to pull down the 2, so we actually get a 16 thirds times x. And we want to set this equal to 0, because that's where we're going to get a critical point. This derivative always exists. We are just dealing with the polynomial, so we don't have to worry about critical points of that sort. But we do need to see where this equals 0. If we go ahead and solve, we can bring the 16 thirds x over to the other side. The thirds kind of cancel each other out, and 320 divided by 16 gives us an x value of 20. Note that this is a critical point of our function. It doesn't necessarily mean that it is our absolute maximum. So recall what we had to do is make a table of values. We basically put in our x values and see what are the values of a that we get out. And remember, we take our critical points, all the critical points that we get, and the endpoints of our interval. We need to pick the 0 and 40. Now, in a lot of these cases, the endpoints aren't going to be too relevant, but mathematically, we still need to consider them, because it could be the maximum is at one of those endpoints. In this particular case, if we plug 0 into our function, in our original a, we do get 0. I mean, everything becomes 0 there. In fact, if we plug 40 in there, we also get 0. It's a little harder to see, but you can work it out. Basically, what's happening there when x equals 0, here we're talking about the links down here becoming 0. And, well, if those links are 0, then we don't have any area to talk about. We essentially get one big long fence, vertical fence. When x equals 40, that's the case when y was equal to 0. In that case, we have one long horizontal fence. In either case, we end up with an area of 0. And we can find that by just plugging those into the function if we wanted to. In the case of 20, if we go ahead and plug that into our function, we're going to get a fun large value of 3,200 over 3, which is approximately 166.7 square feet. Point here is that it is a positive number. It is not 0. It is bigger than the other two. And if that's the case, well, it has to be the absolute maximum of this function on this interval. So the area is maximized when x is 20 feet. Well, technically, you also need to know what y is. Remember that y is equal to this formula in terms of x. So we have 160 over 3 minus 4 thirds times x. But x here is going to be 20. And so we get, what, 80 over 3, which is approximately 26.7 feet. Those are the dimensions that we want to use in order to maximize that area. So notice the key points here. The first thing we do is draw a picture and identify what variables are involved. Then we want to set up a function, the function that we want to maximize or minimize, whatever quantity that we're talking about. If there's extra variables involved, we might have to use additional information to get rid of those extra variables in order to finally get down to a function of a single variable. And then we have to think about the domain of that function. That's always a key point to any sort of maximizing and minimizing kind of problem. And then we use our techniques of calculus to actually solve the problem. Let's do another example of this. We'll look at problem 6. Again, I'm just going to go ahead and read it from the book. A campground owner plans to enclose a rectangular field adjacent to a river. The owner wants the field to contain 180,000 square meters. No fencing is required along the river. What dimensions will use the least amount of fencing? Now again, the book has a drawing of this that I'm just going to kind of sketch out here for us. So on one side we have a river. On the other side we want to make a rectangular enclosure. They actually do already give us some dimensions here, or at least variables for our dimensions. So we get this rectangle with a width of x and a height here of y. And they want us to enclose here 180 square meters. That's what we want to have. But we want to use the least amount of fencing. We want this fencing to be as small as possible. Again, we need to start making a function to optimize, a function that we want to maximize or minimize. Note that in this particular case, unlike the previous example, we are trying to minimize something. Before we were trying to maximize an area, this time we're trying to minimize the fencing. I'm going to just pick F for fencing, the total amount of fencing. If we think about what the fencing is in terms of our variables x and y, well, we've got 2 copies of y and 1 copy of x. They specifically said that along the river we don't have to worry about fence. So we're going to have x plus 2 copies of y. That is the function we want to minimize. Unfortunately, of course, we have 2 different variables, and we need to simplify it down. That's where this area is going to come, or the area of this enclosure is going to come into play. Of course, area of a rectangle like we have here is just the product of the width and height. So our area of x times y needs to equal 180,000. We'll use this statement to actually solve for one of our variables to replace in our function for f. Now, just because we like to work in terms of x's, I'm going to go ahead and solve for y so they can replace y. It technically doesn't really matter. You'll be able to find the answer either way. But I'm going to basically take this and divide by x. So 180,000 over x is my y, which I can then go ahead and put into my formula for f. F is going to be x plus, well, 2 times that. 2 times 180,000 is 360,000 over x. And that is the function that we want to minimize. Of course, we do need to figure out what our feasible domain is. What are the limits on x that can be put into this particular function? Now again, x and y do need to be positive, or not necessarily positive, but at least non-negative numbers. So we're going to say that x can go down to 0. X has to be greater than or equal to 0. Unfortunately, in this particular case, if we did pick x equals 0, it would break our function. And that's just because in this particular case, if we make x equals 0, it wouldn't give us a positive area. It definitely would not give us an area of 180,000. So x equals 0 is not a possibility here. But it also turns out that any positive value of x will give us a positive value for y that would make this work. There's actually no other restriction on x that we can have. So our feasible domain this time is just 0 to infinity, not including 0. Having an open interval like this and having one that goes off to infinity is definitely going to make the final steps a little bit more complicated. That doesn't mean we can't solve the problem, but we have to be a little bit more careful. We can't just make a table like we did in the previous example. Okay, so how do we minimize this function? Well, we differentiate it to look for critical points. That's our very first step. So the derivative of this thing, well, derivative of x is just 1. Derivative of something over x, well, keep in mind this is x to the minus 1 power. Might even be helpful to rewrite it that way if you want to. But with that minus 1 power, we pull out the minus, so we have a negative here. And then our new power, when we subtract 1 from negative 1, we get a negative 2. It's not going to affect the 360,000 that we have on top, but we will have an x squared on the bottom now. When we look for critical points, we need to set this equal to 0. See what we get. That just means that we're going to have 1 is equal to 360,000 over x squared. If I multiply everything by x squared, I'm going to get x squared is 360,000. So that x is equal to plus or minus 600. Well, for one thing, we don't have to consider the minus 600. We're only looking at positive x values. So really, we're going to completely ignore negatives here. X is going to be 600 for this critical point. We also have another critical point technically. Well, I shouldn't say it is a critical point, but it's another. When we're trying to find critical points, we also have to wonder where the derivative doesn't exist. It definitely doesn't exist at 0, but 0 is not in the domain anyways. In fact, it's not in the domain of this function even if we weren't considering the feasible domain. So we only have one critical point at 600. Again, because we're working with an open interval, we can't just make a table. We can't put 600 and our endpoints on the table. What I'm going to do here is actually make a number line. So we'll have 600 on here. Over here, I'm just going to put 0. I don't want to consider anything past 0. And I don't even want to include 0 itself, so I'm going to put an open circle there saying that's not included. So anything from 0 but not including 0 onward, and then 600 is our most important point in there, our critical point. Let's see where, and actually let me go ahead and put this is f prime. We're not actually going to be looking at the second derivative here, but I do want to get you guys into the habit of labeling these number lines in case when we get to the point where we actually consider multiple number lines on the same problem, we don't want to run into any confusion. I'm going to take test points in these intervals. Now, I went ahead and picked some numbers that actually come out nicer than normal. So this is kind of an annoying formula to plug numbers into. So I picked 300 for the interval from 0 to 600. So I have 1 minus 360,000 over, well, 300 squared gives a 90,000. And that actually simplifies very nicely to negative 3. Because 360,000 is actually 4 times 90,000. So this is 1 minus 4. Specifically here, and it really didn't matter exactly what this number was, it just matters that it is a negative number. We actually are decreasing on this interval here. On the other side, I picked 1200. Again, it doesn't really matter what number I pick as long as it is in this interval. I just picked that to make it a little easier to compute. So I have 1 minus 360,000 over 1200 squared is 1,440,000. But the important thing here for calculation is that it is actually 4 times 360,000. And so we get 1 minus a quarter, or in other words, 3/4, which is specifically a positive number. And that's what I wanted. So what we can tell from here, using our first derivative test, is that because it went from decreasing to increasing, we do have a relative minimum at 600. In fact, since our function never really turns around any other place, we know it has to be decreasing down from 0 down to 600 and increasing from that point forward. It never can get back further down than it was at 600. Essentially, you can kind of think of it as you move away from 600, it increases more and more. So it definitely is increasing after 600, but if you're going backwards, our decreasing here turns into increasing away from 600. And therefore 600 is where our minimum is going to be. So fencing is minimized when x is equal to 600 feet Of course, that's only one of our dimensions. That's the length parallel to the river. The length perpendicular to the river, we're still going to have to find. That's y. But y, remember, is 180,000 divided by 600. So 180,000 divided by 600, which is 300. 300 feet. That is our answer. Next problem is 24. Reading 24 from the book, we have an energy drink container of the shape described in exercise 23. Specifically in 23, they're talking about a right circular cylinder. I don't know why they didn't just say that. Basically, an energy drink container of the shape of a right circular cylinder must have a volume of 16 fluid ounces. The cost per square inch of constructing the top and bottom is twice the cost of constructing the lateral side. Find the dimensions that will minimize cost. So let's start with a picture. Our container is going to be a right circular cylinder. Now, most people just refer to this as a cylinder. Technically, here we can actually consider different cylinders that are not circles on the top and bottom, or might not be perfectly straight up and down. They could be at a slant to each other. Most people just refer to this as a cylinder, though, and that's what we're going to be working with. So we have some container that's going to be containing some energy drink, and it looks like this. We want to talk about the capacity of it, because they do ask us to have a volume of 16 fluid ounces. But they're talking about the cost in terms of the material on the outside, which is really related to the area of the outside. So we're going to have to somehow relate those concepts to each other. We want to talk about the dimensions of this particular can. Well, we have a height h, and because we have circles on the top and bottom, those circles will have some radius r. When we want to minimize costs, and the cost is given in terms of the area, we want to build a cost function by just considering the areas of the top side, the side, top, and bottom. Well, the side here, the side of a cylinder, so the area of the side is going to equal 2 pi RH. Essentially, 2 pi r comes from the circumference of the circle, but then multiplied by the height. Kind of think of this as a rectangle just been wrapped around in a circle. The area of the top and bottom well, both of those are just circles. We have a circle on top and a circle on the bottom. The circle on top has an area pi r squared, and the circle on the bottom has the same area. For the actual cost, they haven't actually told us what the cost per square inch actually is. So I'm going to have to make up a letter for that. I'm going to say here that little c is the cost per square inch of the sides, which means that 2c is the cost per square inch of the top and bottom. That means when I set up a formula for the cost, I'm going to take the area of the side times the cost per square inch of the side. So we have 2 pi, we're going to put the c in the middle, times RH. Make sure that's an r, not an n. Then I'm going to take 2c times the area of the top, and I'm going to have to do the same thing for the area of the bottom. So actually I'm going to have two copies of the top and bottom, both with a cost of 2c. In other words, I'm going to have a 2 times 2c times pi r squared, or 4c pi r squared. That is my cost function, at least in terms of the radius, the height, and whatever the unknown cost per square inch of the side actually is. Now, c itself is actually, or the little c itself is actually just a constant. We don't have to worry about replacing that one. But we do have an r and an h. We want to go down to a single variable. And that's where we're going to use the other pieces of information. We're going to use the fact that this container is supposed to have a volume of 16 fluid ounces. So the volume of a cylinder is the area of the base times the height, so pi r squared times h, and that's going to have to equal 16 fluid ounces. But since our r and h are in terms of inches, we want to put fluid ounces in terms of inches as well. The book actually tells us that a fluid ounce is approximately 1.80469 cubic inches, which means that 16 fluid ounces is 28.87504 cubic inches. I'm actually going to go ahead and round off the 04 at the end of that. It's not really too necessary. So we're going to say the volume is equal to that, which means that pi r squared times h is equal to that. I'm going to go ahead and use that to solve for h. So h is going to equal 28.875 over pi r squared. And I'm going to go ahead and put that into my formula for c. That does mean that what we have here, we're going to divide this by pi r squared and multiply it by 28.875. 2 times that is actually 57.75. We still have the little c in there. The pi actually cancels out, and the r on here actually cancels one of the r's here, so we're left with a single r on the bottom. This term here is unchanged, though. We still have a 4c pi r squared. This is the function that we want to minimize. We do need to figure out what is the feasible domain, what are the limits on r, but this is actually pretty similar to the previous example. We want r and h to be non-negative, but our function doesn't allow us to have r equals 0, but any positive value of r is going to result in an h that works in the problem. So our feasible domain is going to be the same as what we had before. It's just going to be 0 to infinity. Unfortunately. But that's what we got. So we're going to go ahead and differentiate this thing. So c prime of r, our variable this time is r. Keep in mind here that little c is actually a constant. That's not going to change, so we do not have to use the quotient rule here or the product rule here. We have some constant over r. Well, remember this is r to the negative 1 power. We're going to do the same kind of stuff that we did on the previous problem. We're going to get a negative from the negative 1 power, and then we're going to change our power to a negative 2. So we have a square on the bottom. Over here, this is a lot easier. We have 4c pi, but all that's a constant. We're differentiating r squared. We end up getting to pull out that 2, which will change the 4 to an 8. And we're just left with an r. So this is our derivative. If we set this thing equal to 0, this does require a little bit of work. I'm actually going to go ahead and since we have essentially a difference between two things, I'm going to set these things equal to each other. We have 8c pi r is equal to 57.75c over r squared. Going to multiply each side by r squared, but divide by 8c pi. That means we have an r cubed over here. Combine that r squared with the r. We have a 57.75. We actually divided that c out. That c went away. That's the reason why they didn't give us a value of c. It technically does not change what the r value is going to be. But we still have the 8 pi on the bottom. Now, I actually do want to know what this r is, so I'm going to go ahead and work this out using a calculator. This is approximately 2.2978. And when I take the cube root, I get approximately 1.32. Of course, we also have a potential critical point when the derivative doesn't exist. It doesn't exist when r equals 0, but again, that's not in our domain, so we actually don't have to worry about that one. If we make a number line, like we did before, we start at 0 here. We have an r of 1.32 in the middle here. We go ahead and take the value of c at test points. Around 1.32, I go ahead and just pick 1 and 2. 1 for this first interval, 2 for the second interval. I just went ahead and used a calculator for this. Keep in mind that each of our terms here does have a c in it, so actually what we get from these actually will have a c in them. For c prime of 1, I got an answer of negative 32.617 times c. Of course, c is a positive number, so this is going to be a negative number overall, because that is being multiplied by a negative. For c prime of 2, I get 17.562 times c. Again, this is a positive because we're taking a positive number times the positive c. So we get a positive there. So this is actually very similar to our last problem, where we had a single critical point, where it's a relative minimum because we're decreasing and then increasing. And so we end up with an absolute minimum at this point. So cost is minimized when r equals 1.32 inches. Remember that we're doing this in inches. And of course, h, we do need to know what the height is. Our height comes from this formula here. We have 28.875 divided by pi r squared. So 28.875 divided by pi times 1.32 squared. Again, use a calculator for this. It comes out to be approximately 5.275. And that's again inches. So we have a height of 5 and some inches and a radius of the top and bottom of 1.32 inches. And that will give us a minimum cost in constructing that particular container. Now, I kind of apologize for this video being so long. These problems can actually be kind of time consuming. But I do want to do one last problem that is not a area or volume problem, because we've been kind of repetitive on that. That's kind of the fault of the book. It doesn't really have a lot of other problems to work with. But I'm going to work on problem 36. A home gardener estimates that 16 apple trees will produce an average yield of 80 apples per tree. But because of the size of the garden, for each additional tree planted, the yield will decrease by 4 apples per tree. How many trees should be planted to maximize the total yield of apples? And what is that maximum yield? Well, the first thing, we don't really have a helpful picture to draw. I could maybe draw like a box here and put little squiggles in it to denote trees, but that's not really going to help us solve the problem. What we do need to do, though, is give letters to the things that we're working with. I'm going to pick a capital Y to be the yield. This is the number of apples that we're going to get from this garden. And I'm going to make it a function of t, where this is the number of additional trees. Now, technically, we could write this in terms of just total number of trees, but because everything is kind of worded in a way where we start with 16 trees and put additional ones, it actually will make it a little easier to make our function if we do t as additional trees. So when t equals 0, that means we have 16 trees. When t equals 1, we have 17, and so on. It's just a different way of phrasing the problem. But we know when t equals 0, when we have 16 trees, then we have a total number of apples of 16 times the 80 apples that they tell us we're going to get, which comes out to a fun 1,280 apples. Having t additional trees, will make the number of trees that we have different. It'll change that to a 16 plus t in this product, but it'll also change the number of apples per tree. It'll decrease this by 4 apples each time. That's what they're telling us is true. So we're going to have to take 80 minus 4 times t. And that means that if we work this all out, we get 1,280 plus 16t minus 4t squared. I just FOILed this thing out. This is our function that we are going to maximize. We want to maximize our yield. We want as many apples as we can. We do need to find out what is the feasible domain. At least this time we didn't have to find another equation in order to eliminate a variable. We only had the yield and the trees to begin with. But we still need to find our domain. How many trees can we have? Well, theoretically, we could have fewer than the 16 that we're talking about starting with. We could have maybe increased our yield by actually having fewer trees, but having those trees actually produce more apples. We could go all the way down to having no trees. We can't go negative. We definitely can't have negative trees. So we'll go down as low as 0. Well, not 0, because t equals 0 says 16 trees. We're actually going to go down potentially to negative 16. Might seem a little weird to have it happen that way. That's just a product of how we started the actual problem. Now, what's the maximum number of trees we can have? Now, we don't get information about how much space there really is. So we don't know for sure that there is a limit because of the space in the garden. But we could think about what is the ultimate conclusion of our formulas that we're talking about. What could go wrong? Well, we can't have a negative number of apples per tree. So we don't want this 80 minus 4t to ever go negative. When is this actually equal to 0? Well, 80 minus 4 times 20 does equal 0. So if we get to 20, we can't go to 21. That will give us a negative number of apples per tree, and our formula is just completely broken. Now, obviously, our particular formula here probably is broken anyways. If we had those 20 additional trees, probably would have at least one apple somewhere, but we're taking their formula to its extreme conclusion. We definitely can't go past 20 additional trees, or things would be completely broken. So this is going to be our feasible domain. And it is a closed interval. We're in a nice situation here. Okay, so we're going to maximize this particular function over this domain. Of course, we go ahead and find their critical points. Y prime of t, the 1,280 goes away. 16t becomes a 16. Negative 4t squared will become a negative 8t. If we set this equals 0, of course there, t equals 2. Probably shouldn't even have to worry about doing that step by step. 16 minus 8 times 2 is 0. And so t equals 2 is our critical point. We don't have to worry about the derivative not existing. It definitely exists everywhere because we're dealing with a polynomial here. Because we have a closed interval, we can go ahead and make a table. We go ahead and put 2 on our chart when we have our endpoints of negative 16 and 20. Now, you can actually reason out what the values of y are going to be at negative 16 and 20. They're actually both going to be 0. When we have t equals negative 16, we have 0 trees, and it doesn't matter how many are produced per tree if we don't have any trees to begin with. So we get 0. But it will be 0 when we plug negative 16 into this formula as well. Same thing with 20. We found this 20 at our endpoint because that's when our our number of apples per tree goes down to 0. So it doesn't matter how many trees we have if they're producing 0 apples. So that's usually what happens when you're dealing with these feasible domains. If we have endpoints, they're usually places where things go to 0 anyways. Especially when we're doing a maximization kind of problem. At 2, however, if we plug 2 into our formula here, we have 1,280 plus 32 minus 16. Overall, we get 1,296. So a positive value is definitely bigger than the other ones. So we do get a maximum yield. So we have a maximum yield of 1,296 apples when there are, well, how many trees do we have? Keep in mind, we don't have 2 trees. We have 2 more than the 16 that they started with in the problem. So we actually have 18 trees. And that's our answer. So there are a few things that were kind of maybe a little strange to do, like making our variable be the number of trees past 16 and all that kind of stuff. But the process is still the same. We identify what variables we're talking about, the y and the t. We find some way of turning that y into a function of t, some formula, and identify what's the domain of the formula. Then we use our techniques of calculus to actually find the maximums and minimums of that particular function. Alright, so quite a long video. We only went through 4 examples, but hopefully you got an idea of what we're doing in those examples. In the next section, next video, we will go through some applications that are basically just the same way, but these will be more focused around business and economics. So we'll also even define a couple of particular terms that are useful for economics in that particular section as well. So I'll see you guys in that video as well.